Thanks for coming. I'm really honored to be here at this really wonderful facility and having been invited. This is really great, and thanks for coming to hear me talk. You see the title of the talk. We're going to be talking about network coding. I should start off by saying that this is work that I've done together with several different students and a collaborator at Drexel. So my student, Songduan Lee, has graduated, and now he's a postdoctoral fellow at the Institute for Network Coding, working with Raymond, and then he was co-advised with Steven Weber. My student, Jean Apte, is still a candidate. He'll try to wrap up by the end of this year, as will Yunshu Ye. Jean Apte contributed to the network symmetry and some of the software we're going to be talking about. Yunshu has contributed to the nonlinear part of the entropy region we'll very briefly touch on. And a lot of the work we'll be covering is Songduan's work. Okay? And as I said, Songduan is co-advised with my colleague, Dr. Weber, so he has his imprint on this as well. All right, so let me give you some motivation for the problems. The research all spirals around the following idea. I have a network coding problem, and what this is going to be for me is a series of independent sources and a directed acyclic hypergraph, okay, that and then a series of sinks in that directed acyclic hypergraph demanding subsets of sources. And the idea is I want to be able to take that problem, put it into some software, and get a rate region, okay? And the rate region will be a polyhedral for me, because I'll be working with bounds that will always be polyhedral, cone jointly in the variables describing the number of bits that are going on each of the edges, those are the R's, and the number of bits for each of the independent sources, those are the H's. Okay?
You said hypergraph, but I don't see how to think about hypergraph.
Each one, so the reason why we have a hypergraph instead of the normal graph model is that in many cases the same message, identically same message, is going to be overheard by multiple people. Okay?
I see links across the connect nodes. So when you say
this edge is a hyperedge. It's a directed hyperedge between 4, this edge 4 here, for instance. Yeah. The same random variable is going to be on that, the same message, and it's going to be overheard by 5, by this node here, by this node here, by this node here. So I'm keeping track of that. And in the classic formulation, you have just directed edges. It's easy to transform that problem into this one, but that transformation is messy, and it involves removing some variables. So we're just going to draw it this way because I'm going to have to enumerate things, and I want to keep it small. Do you follow? Okay? All right. I'll explain that. Yes, so that's a key part of the talk. We're going to talk about how it works. Okay? And the idea is that this rate region is going to describe over all possible ways. So this sets up basically who can hear what. Okay? And an outgoing edge from a node, right, will be some function of all the incoming edges. Okay? And what I'm interested in is over all possible ways of encoding, doing that local coding at each node, and decoding at each of the sinks. What are the fundamental relationships between the rates on the edges and the entropies of the sources? Namely, if I have a point in this region, there should exist a code which achieves that point. And if I don't, if the point that I try is not in that region, there should not. Okay? All right. And so, of course, that's a polyhedral cone. All right? So, by the way, it's not always necessarily going to be polyhedral, but I will be using Polyhedra to approximate it. Okay? And so what I'd like, of course, since it's a polyhedral cone, there's both an inequality description and an extreme description of that cone, right? And so both in terms of its inequalities and its extreme rays, okay? And the idea is for each inequality, I'd like the software to generate me a human-readable proof to justify that inequality. And I'd like the software to generate me for each ray a code which achieves that ray. Okay? It's a tall order to fill. Okay, but that's what we'd like to have. It's the ideal picture. And where this comes from, the fact that this is even something we would conceive of, it comes from a nice result from Yan, Young, and Zhang. It goes back farther than this, but this is the trans-IT version. That says that were I to know this region of entropic vectors that Laszlo was speaking about yesterday morning, and you'll hear more about, then I could take that region, intersect it with a series of constraints that come directly from the topology, who can hear what. They're very intuitive. So for instance, the conditional entropy of 5 here, given 4, 1, and 3 should be 0, and so on. Okay? And intersecting it with constraints like that and projecting it. And there's some other things here. We have a closure, but we'll handle all of that in a bit. Okay? So this, in principle, is what we're going to exploit by plugging in polyhedral inner and outer bounds to entropy, at least in principle, and calculating the associated region. Okay? And, of course, immediately look at this. If we're going to follow that computational agenda directly, you can already see that this is going to be limited to fairly small problems, because this polyhedron here has an exponential number of variables in the sum of the number of sources and the number of rates, the number of edges in the network. So you're going to be able to only do small problems with this. Okay? And so bearing that in mind, here's the agenda for the talk. The first thing that I want to do is I want to explain how can this piece of software work, okay? Both from the perspective of a converse and achievability, so outer and inner bounds, constructive outer and inner bounds to the rate region, okay? And then checking to see if they match. Okay, then what I'm going to try to do is push the computer as far possible as it can, get as big networks as possible by exploiting problem symmetry. So I'm going to have to define what problem symmetry is and explain how to exploit it. Okay, and then at that point, the goal will be to show off by solving as many problems as possible. Okay, and so then that changes the lens to listing problems that are different from one another and in a sense canonical and minimal. So that'll be the third part of the talk. Okay, and then the fourth part of the talk is by the time you're done with that, you already have hundreds of thousands of equivalence classes of networks that are, even though they're fairly small, you can see it from the graph model, right? This is a rich model. There's going to be a lot even for small problems. Okay, so you're already going to have that, and there's a lot of interesting ones in there, but you can't read hundreds of thousands of rate regions and proofs, so you got to learn from this database somehow. And furthermore, you'd like to say something about networks that don't have 2 sources and 3 edges, ones that are a little bit bigger with it. And so we'll do that by endowing a problem hierarchy. Okay? Both of those things. Okay. So first, let's talk about how this software can work. All right, so again, from the perspective of at least a high level of what we're doing, we're going to take an outer bound to the entropy region. This will typically be the Shannon outer bound or the polymatroidal axioms. Okay? And we're going to intersect it with those constraints, and we're projecting it onto these rates and these entropies. Okay? And polyhedral projection, remember, the first thing that we learn in school in order to project a polyhedron is Fourier-Motzkin elimination. And it's very clear that you do not want to use Fourier-Motzkin elimination in this problem. It'd be hopeless. What Fourier-Motzkin does, if you're not familiar with it, maybe that's why you're laughing, you isolate a variable. So you're trying to eliminate variables one by one. So you look at every inequality where that variable has a positive coefficient and every inequality where it has a negative coefficient. And that forms an upper and lower bound on that variable. You then eliminate the variable by putting the upper bounds less than the lower bounds. Okay? And you do that one by one, removing redundancy. Now the issue with that is, remember, we have a space that we're starting with which is exponential in size in the space that we're trying to get to. And so those intermediate polyhedra, as I remove those variables one by one, I have an exponential number of those variables to remove. Okay? And those can be far more complicated than the ultimate projected polyhedron. So you want to work with methods that work and build up directly in the projected space. Okay? And people have been talking about this a while. Of course, we've discussed it for non-Shannon inequalities. You have a similar issue there when you're following this agenda for generating them. Okay, and what we've settled on that works just fine for the rate region problems that we'll be showing is this Convex Hall method. It's very visual. Let's describe the way it works. So suppose that this is the polyhedron that is the projection. So remember, I had a cone. I'm going to turn that cone into a polytope simply by taking the rates and the entropies and saying that they should sum less than or equal to 1. Okay? That's an inequality that I've now added to the projected polyhedron, and it's the only bounding inequality, and I haven't made the polyhedron any more difficult because I've just taken the extreme rays and I've scaled them now to sum to 1. Okay? They're all positive, their coefficients. None of them can sum to 0. Okay?
These things come directly from the network you're starting with. Is that correct? So if you have a description of the network,
I have inequalities that come from entropy that are generic, and then I add to that equalities that are from the network. Okay? And then that, of course, those equalities make my original high-dimensional cone reduce in dimension somewhat. Okay? And then I have to take that still reduced cone and project it down to just the variables I care about. Okay? So it's like quantifier elimination. Sure, that was on the previous slide. I can do that. You're right, and I verbally said that a moment ago. So that's here. Sure, this is hard to read. Why don't I do that? Okay, that'd be fine. So basically what this says, they're all fairly intuitive. I mouthed off about that in the beginning, but I should explain it now. Okay, the key idea is that since the sources are independent, their joint entropy should be the sum of their marginal entropies. Okay. Furthermore, since I am supposed to be able to create at a source the outgoing edges, or at an edge, at a given node, the outgoing encoding from everything that comes in, the conditional entropy of what comes out of a node, given what comes into the node, should be 0. And then add a decoder, again, same inequality. The conditional entropy, or same equality, the conditional entropy of what I'm trying to decode, given what came in, should be 0. Okay? So that's all these constraints say.
But how do you encode the fact that you have a hyperedge or anything like that? Is it just because you're reusing certain variables? Or?
Yes, you're reusing certain variables, and the polyhedron I'm intersecting this with considers every possible subset entropy. So these form linear constraints in the subset entropies. Okay? All right.
Okay, so you basically have a variable for each, a random variable for
each edge and each source.
Okay. And then you're taking.
And then the power set of those, each element in the power set has an entropy. There's some equalities that occur in that vector, which is now the power set of those nodes. So it's a very high-dimensional polyhedron. Okay? So, all right. And so this is a generic method for polytope projection, okay, that you can use for this problem. All right? It's fairly visual. So imagine you first get a full-dimensional inner bound, and then what you're going to do is you're going to build up this inner bound, build up progressively better and better inner bounds to the projected region by keeping track at each time of which facets you know are terminal. And what it will mean for a facet to be terminal, this is again in the projected space. So you'll run a linear program with the cost vector associated with the inequality associated with this facet. And you'll take the cost vector and you'll put in zeros in all of the dimensions you're projecting out. And if when you're done with the LP, you get the right-hand side in the current inequality, this becomes a terminal facet. If you don't, you have a new extreme point from simplex in the high-dimensional space that you can project down to be a new extreme point of your inner bound. You add it, you update your inequality description, and you continue until all of your facets are terminal. Okay? So for instance, it's the under facet that we did here. We got this ray next. Then we did this outward going facet. We got this extreme point. We did the back facet. We got this one. We did the bottom. We got this one. Now all of the facets can be checked, and they're the correct answer. Okay? And so we've implemented this because we needed a proper method of polyhedral projection. Because we're trying to prove things, we also used a rational version of simplex when we implemented this so that we don't have round-off error. Okay, and so that's a nice thing, and you can get it from the software section of our website. Okay? Then that's used in the subsequent package that I'm talking to you about right now that tries to do rate region calculations. And so here's a sample session with that. Basically, I described that original network that I showed you at the beginning slide via this encoding. It's a bit of an awkward encoding, but it works well with MATLAB. I can explain how to do that if you want offline later. There's good documentation. And this says I want the outer bound. I call that from MATLAB. It creates the associated polytope. It goes over to the C program. The C program projects it. Then I present the projected polyhedron, and lo and behold, the inequalities I get in the projected polyhedron are those that I started with. The other ones are simply that the rates and the entropies are greater than or equal to 0. Okay? So there's that. If you want to use that software, you can. All right? Achievability. How does that work? This is a little bit more complicated. All right? We've been through a number of different achievable constructions. Let me talk to you about the one that we're doing currently. Okay? So we'll start by focusing on linear codes. Okay? And so what happens in a linear code? So what comes into a particular node in the network will be vectors over a finite field. And what will go, and the dimension of those vectors is associated with the rate on each of the edges that's coming in. And what will come out will also be a vector. Again, dimension integer equal to the rate that's coming out. Okay? All right? And there are these local encoding matrices which take all of the vectors that come in and map them to the message that go out. Okay? And first thing that you do is you propagate. It's a directed acyclic hypergraph, so you can propagate through these local encoding matrices and get global encoding matrices that describe each edge in terms of the way that they relate to the incoming sources in the network. Okay, so now I have these global encoding matrices. And the key thing to realize is that for the rate region calculation, owing to the Yan-Yung-Zhang result, all that matters is the entropies, the joint entropies of the edges. So if two collections of global encoding matrices give me the same subset entropies, then I don't need to consider those as different. They do the same thing for me rate-wise. Okay? And when I look at those subset entropies, those are determined by the rank that's achieved by stacking or concatenating the associated global encoding matrices. And that rank in turn can be thought of as take the span even further of the columns of each of those global encoding matrices, okay, and create the subspace associated with that. And that rank is then the dimension of the sum of those subspaces. Okay? So again, two global encoding matrices whose span gives me the same subspace are going to give me the same entropies. So don't consider them as different. Okay? And so what you really have, if you're trying to list all possible codes for a network, is the following sort of structure. You have a set of subspaces and a map which assigns each of those subspaces to some edges, possibly more than one in the network. Okay? And from the standpoint of listing all codes over a particular field up to a certain dimension, okay, then what you have is you want to list what we'll call canonical representatives under a group action. So let's explain that. The next thing to realize is that two sets of subspaces will again give you the same subset entropies if they're related through some element of the projective general linear group plus field automorphisms. That's why there's a gamma, not PGL. Okay? So if I have any element of this group, and I take a set of subspaces, and I act on them by that element of that group, then the other subspaces I have will have exactly the same subset ranks, dimensions. Okay? And so I want to remove that equivalence. So that group action then will form orbits in the set of subspaces, and I want a transversal of those orbits, one representative from each orbit. Okay? Furthermore, so here's the picture. We have all the subspaces up to some critical dimension d, less than or equal to the maximum rank that we're going to have for a singleton in here. Okay? And we have the subset of the power set associated with subsets of size L, say, that are going to be the distinct subspaces we have. This will be less than or equal to the number of variables in the problem, i.e. the number of edges and the number of sources. There are equivalence classes in those subspaces, subsets of subspaces. Okay? And for some of those equivalence classes, there's going to be a way to map the subspaces into the network and obey the constraints of the network. For some other ones, there won't. We only want the ones where there is a way to do that. Okay, so we want a transversal of those orbits where there is a map into the problem to obey the constraints. That's the full enumeration problem. Okay? And so for small problems, you can use some generic tools from group theory to help solve this. It's very similar to a problem that was studied in a book called Linear Error Correcting Codes Classification by Isometry by Betten, Brown, Frippertinger, Laue. They're all students from a university in Germany, Bayreuth, working with Adalbert Kerber at various times. Kerber's written a number of books in the theory of group actions. So when you look at these algorithms to list non-isomorphic representatives, he's pretty well known in that field. Okay, the generic structures for that. Okay, we can talk more about that, but I don't have time. All right, so the idea is the generic problem that we have here is we have a set, and we have a group acting on that set, and we want to know the orbits in the power set of that set, and the orbits in the subsets of size L. And we don't want to do that with generic group computations because that's god-awful. Okay? So we want to use the fact that we can do pointwise orbits within the group on the set to help us do, and the group and its subgroups on that set, to help us do the orbits in the power set. Okay? And this algorithm Leiterspiel lets you do that. Okay? So what it does is it lets you, at every time, it's keeping a transversal, one element from each equivalence class, of the orbits of size I. And it then intelligently extends those into the orbits, canonical representative of the orbits of size I plus 1. Okay? And it additionally, think of, there are all sorts of extension problems that are like this. You can extend graphs, you can extend matroids this way. Okay? And the idea is you're always keeping around not just the transversal, the canonical representatives, one from each orbit, but also their automorphism groups. That's key. You keep that in the structure. Okay. All right. How does that map back to our problem? Well, very simple. Now, I should tell you one more thing. The algorithm lets you have a test function. So if you're interested in only those orbits which have a certain property, as long as that property is preserved under the isomorphism, and inherited in the sense that if I don't have the property, then any superset of me shouldn't have that property either. Then the extension algorithm, it's clear, it's an extension algorithm, it's augmenting, is able to handle that by cutting off that whole list of extensions at that point. Okay? So for us, that property will be, is there a way to take the set of subspaces I have thus far and map them into the network and obey the subset of constraints involving what I've defined so far in the network. Okay? All right, so that's what's implemented. It's an enumeration algorithm, right? It's not, I have a rate vector. Let me ask if this rate vector is solvable. It's enumeration. List all possible rate vectors from this code. Okay? But you can treat it as a verification algorithm. And that, well, I don't really know why my student decided to do that first. I think to make it more compatible with other pieces of software. But that's available in ITAP. And we also have the enumeration exposed to you in ITAP. Okay? So this is a piece of software we've released to play on, of course, information theoretic inequality prover, information theoretic achievability prover. Okay? And this will sit there and it will take a rate vector and a description of a network. Okay? A rate vector, the one we have down here, and a description of a network, which is an encoding of this graph, okay? And a field, an answer, definitively, yes or no. Not just yes when there's yes, but it'll also tell you no when there does not exist a code over that field size, okay? All right? Now, the classic way, I don't have much time to talk about it, but the classic way you would have done verification in network coding is you can build a system, an ideal, by considering local encoding constraints and decoding constraints, the matrices used to do them as variables, propagating through the network, and requiring the ultimate global encoding matrix to be 0 in the right places and 1 in the right places. Okay? You then ask whether or not that you ask whether or not that ideal is empty or not using a Gribner basis calculation. Okay? People have simplified that. That was already in Kutter and Medard, 2003, this method. Okay? People have simplified that method to use as your variables, instead of the local encoding matrices, something called path gains. Okay? So you look at a path between a source and a destination. That becomes a variable, and you have constraints on those. The good thing about that is it takes the Gribner basis, which in the Kutter-Medard formulation, the terms in the polynomials can have very high degree. The path degree formulation keeps them down to degree less than or equal to 2. But anybody who's ever played with the Gribner basis package knows that while this is one of those algorithms which provably finishes in a finite number of steps, very small problems take a very long time. Almost always. Okay. And it just so happens that this intelligent form of guess and check, especially when you have rates on edges that are greater than 1, can be faster, empirically speaking. We have them both coded up and exposed to the user. Okay? All right. One last thing about achievability before we move on. I wanted to put this here because Laszlo is here. At least in principle, the same recipe can get you small nonlinear codes. How does that work? Okay? Think of a random variable. All these random variables are discrete. Okay? So it's clear, a random variable formally is a map from the sample space into a series of outcomes. Right? The inverse image of that then forms a partition. Right? Okay? And that's the right way in terms of entropy to think about the random variable, because it doesn't matter what those outcomes were labeled. Those don't affect what the entropies are. Okay? And it shouldn't matter which variable I labeled variable 1 and variable 2 and variable 3. So really what I have when I'm considering entropies for discrete random variables is a set of set partitions. Okay? Furthermore, it shouldn't matter what I've labeled as 1 in the sample space, 2 in the sample space, up to k in the sample space. So if I'm considering all possible supports, if you will, for random variables, then what I want is the orbits in the set of subsets, set partitions under the symmetric group. Okay? You can do that for small problems. All right? And we've used that together with numerical calculation to calculate the pyramid that Laszlo passed around us the other day. Okay? I think it's below his. Okay? But these are small support distributions. All right? And certainly they give you Ingleton violation and they improve your capacity. Okay? And you could also take that same algorithm and add, again in the extension process, checking whether or not there's a way to map into the network, okay, in order to turn it into a code enumeration problem as well. All right. All right, enough about that. That's how the software works. So we had a demo for both Converse Achievability, right? Software for both. Showed you where to get it, talked about how it worked, and showed that it does at least work for small problems. Okay? All right. So the next theme is, how do I take this, inherently something that's tuned to small problems, and push it as far as I can, okay, in terms of the size of the problem? And one of the things that information theorists almost always do, you think of the Demacus storage result, or you think of the single source network coding results, or if you think of symmetric multi-level diversity coding systems. We are consistently using symmetry to help us prove these rate regions. Okay? To reduce the complexity. So let's try to formalize that. All right, so think of a network. Let's find a way to encode it. All right, so that the group action will be clear. So you're going to think of a network. You'll have a series of sources, 1 to k, and a series of edges, k plus 1 to k plus e. Okay? And those labels have got to go on the hypergraph in order to describe the network to the computer. But immediately those labels hurt you, because two things that are equivalent look different after labeling. Okay? All right, so how do I encode, if I have those labels though, how do I encode it? So for instance here, the edge 5 is created from the source 1 and 2. So you have 5, edge, define it from source 1 and 2. Okay, down here, 2 is decoded from source 1 and edge 3. 2 is defined from 1 and 3. Group those into two subsets, Q and W. Q has the property that each edge should only be defined once, whereas in W, the same source can be demanded by more than one sink, of course. Okay? And now it's quite clear to see how we're going to act on this. We have the symmetric group, which is going to permute the labels of the sources. And we have the symmetric group, which is going to permute the labels on the edges. Okay? And of course, there's a stabilizer subgroup of that group, which stabilizes the subsets that we have. That forms what's called the network symmetry group. Why do we care about that? Okay? Well, it's stabilizing by construction the constraints that we're intersecting with entropy when we project. It's also permuting the indices of the rate vector in the projection. So it's also a symmetry of both the original polyhedron and the projected polyhedron. Okay, that's key. It's one reason to care about it. So in this problem, you can see I can easily swap 3 and 4. It's clear that that's the exact same set I would have if I swapped 3 and 4. Right, you can see it visually. And independently, I can swap 1 and 2. Okay, so this group has ordered 4, and that's the symmetry group for this problem. Okay? So one of the reasons that we care about is it gives us symmetries of the original and the projected polyhedron. The other reason we care about it is that it gives us isomorphs as well. Right? Okay, so any other element from this group that's not in the stabilizer subgroup will relabel the edges. But those problems are equivalent to one another up to labeling. So we don't want to consider them as different. Okay? So the number under something called the orbit stabilizer theorem, most first things you encounter when you do group actions, okay, is the number of these isomorphs is take the order of the group you've got and divide it by the order of the stabilizer subgroup. That's the number of distinct isomorphs you're going to have. So it helps you count the size of the equivalence classes as well. Okay, so in summary, very simple construction. Gives you symmetries of the rate region, symmetries of the polyhedron you're projecting, and it gives you the number of equivalent networks. All right. How do you use it? Okay, 3 ways you can use it in CHM, okay, in a polyhedral projection method. First of all, when I get a new extreme point, I know all the isomorphs of that extreme point will be extreme points too. Okay? Second of all, when I update the inequality description, again, because of the way that the group acts, I can use the symmetries there to be smart about augmenting additional inequalities I can infer. Okay? For here, you can refer to a nice thesis about how to do representation conversion in polyhedra with symmetry by Thomas Rennes at the Universität Magdeburg, and he also has a software package that you can do that with called Sympol. Okay. All right. This is perhaps the most exciting one. So we've reduced the number of LPs because, again, we know once we get a new extreme point, we know all its isomorphs there. We've reduced the complexity of the inequality updates. And furthermore, we've reduced the dimension of the LPs because when the cost I have, I can take the subgroup of this symmetry group that leaves the cost that I have fixed. Okay? And then it's going to suffice to work in the fixed space from that subgroup. I'll get the same answer running the LP over the fixed space. Okay? So often with polyhedral projection literature, the way that you calculate complexity is you consider number of LPs you have to solve and their dimensions. Okay? So here are 6 highly symmetric problems. Okay? And the number of LPs that you would have to solve before you considered symmetry versus dimension. So all the blues, each one of them would have had to be 64. That's a 6-variable problem. Okay? And you're seeing that you at least have the dimension and typically have the number of LPs for the highly symmetric problems. So you can reduce your complexity somewhat that way. How to use the symmetry group when you're doing the achievability process? You can also use it there. When you go to consider ways to map the set of subspaces into the network, you now have network variables that are equivalent to one another, essentially. Okay? So you can remove some isomorphisms in those mappings. It removes certain things you don't have to consider. Okay? All right. All right, so that's how that works. All right. Let's move on. So let's talk about now showing off. Let's make a big list of solved rate regions. Okay? So to do this, we want the computer to reach as many problems as possible. So we're already going to be thinking about equivalence classes again for the network coding problems. Furthermore, it's easy to set up. One of the things that's a little bit annoying about the way these are often set up is it's easy to add garbage to a network coding model. Let's look at this. Okay? So for instance, let's look at this here. These 2 sources are available at the same node, and they're demanded by the same decoder. Well, it's pretty obvious that I can get the rate region from this, from the one where I combine them into one source. Right? So there are 13 of these. We've come up with 13 or 14 of conditions like this. where you remove garbage from the problem and you can explain the rate region before when the garbage was there from the rate region afterwards directly. Okay. So that's minimality. But then that's just one notion of equivalence. Beyond that, of course, we still have the symmetry equivalence, and we want just one canonical minimal representative. Okay? So what you want is an algorithm which is going to directly list these canonical minimal representatives so that you can then calculate the rate region for each. Okay? We can use Leiterspiel to do it. It's our can opener. It's solved everything for us today. Okay? So Leiterspiel can do this too. Okay? And indeed, what I'll be talking about for the rest, no more plugs for software. This is the last one. But the remainder of the talk, you can download the software to do the things that I'm talking about there on the website as well, including this enumeration algorithm. Okay? All right. So big picture, we're going to list all networks up to a certain size. We're going to put them into our rate region software. Each one, we're going to calculate its rate region. Okay? Put it in a database. Now I have a database of networks, their rate regions, or equivalence classes of networks, actually. Their rate regions, both in terms of inequalities and equalities, a converse proof, each inequality, code for each ray. Okay? And, of course, there's a potential for some of our inner bounds not to meet our outer bounds, in which case the database can also include inner and outer bounds. It just so happens on the ones that we've got now, we've closed all the cases. Okay? So, our first shot at this, more than 2 years ago, looked at a subclass of networks called multi-level diversity coding systems. They don't have any intermediate nodes, and there's a prioritization amongst the sources. So if I'm decoding source 2, I also decode source 1. Okay? So it's a restricted class of networks. There are reasons to look at it. Okay? And we had about 7,000 equivalence classes that we solved there with the software, corresponding to about 100,000 networks with isomorphs. Okay? And now our database has about 700,000 solved equivalence classes, corresponding to about 2.3 trillion networks with all the symmetry and all that. Okay? All the isomorphs. All right, so what now? Well, nobody's going to be impressed. You certainly aren't going to submit 744,000 transactions papers. You haven't learned anything yet. You just have a big database. And you can't sit there and read 744,000 rate regions, realistically speaking. You may be able to pick some. You may be able to query it and look for counterexamples, try to come up with some theory. It's good for that, right? But even that's going to be hard. It's such a big scale already. Okay? Almost you hurt yourself by bragging, by having too many. Right? So what do? Well, you need to analyze, learn, and explain something. And the way you're going to do that is through structure. Okay? Through hierarchy. All right? So we're going to look at two different notions of ways to endow this structure. Okay? They're inspired by the fact that network coding rate regions, in a sense, generalize matroids. They are involving a series of matroids. And matroids generalize graphs. Okay? And in graphs, a crowning achievement in graph theory is something called well quasi-ordering. It says that if I have any family of graphs that's closed under taking minors, it has a finite list of smallest graphs which it cannot contain via minor relationship. Just by the structure of the operators. It has nothing to do with the class of graphs, just by the structure of the operators. Okay? Does not hold in general for matroids, but if I ask for representability over a particular field, this is called Rota's conjecture, it's claimed recently proven. Okay? And they've put a notice in the notices of the AMS about how they supposedly proved it, although there'll be 300 or more pages probably to come out with a detailed proof. Okay? All right, so inspired by that, let's try to come up with minor operations. So what does a minor do? It takes a big problem, finds a small problem within it. Okay? It's a reduction. All right? We're going to do this two ways, in a pessimistic way and in an optimistic way. In a pessimistic way, we're going to come up with an embedding operator. How is this going to work? I'm going to have a big network. I'm going to imagine I have its rate region. I'm going to find a small network either implied or contained within that network. Okay? I want to be able to directly get the rate region from the small network from the rate region of the big network. Set some rates equal to 0, project some rates out, you get the idea. Okay? And the key thing is I want that operation to work not just for the true rate region, but also for classes of codes, such as linear codes. okay, over a particular field. Okay. So this is what we call embedding operators. Well, that's pessimistic in the sense that those problems that are not in my it helps me organize my database, and I can point to things in my database and simplify it. But my database still contains small networks. And I'm not really saying anything about big networks when I do that yet. Okay? So I also need a way, well, I am saying something about big networks, but it's pessimistic. It's saying, hey, that big network you've got out there, this class of codes won't suffice for it because it has this small network contained within it. Okay? That's a pessimistic result. What you really want to be able to do is solve a big network by putting together solutions in your database. And that's what this other set of operators do. Okay? Take two problems you have in your database, paste them together, directly get the rate region from the pasted together version from the rate regions of the small ones. And the key thing to realize is that while both of these are going to be very simple, remember operation of deletion and contraction is also very simple. Okay? And second of all, they can work together because I'm able to calculate the rate region both through getting bigger and through getting smaller. And they do not undo one another here. Okay?
Do we have any example of a composition theorem that says take two, make also a certain kind, take the rate region and put them together?
I will have it in a moment. I'll give you one, but you're gonna, once you see it, you're going to say, oh God, that's obvious. It's not complicated. I'll show you. Okay. The complicated ones, and I can explain about that in a moment. All right, so let me put it together. It'll be immediately obvious once you see it. Okay. So let's start with, just because of the ordering I introduced in this, let's do embedding first, but I'll get to you. Okay, I promise. Don't zone on me. Okay. Simple problems here. Okay. They're all inspired by deletion and contraction. I can get rid of a source. I can get rid of an edge. I can contract an edge. Right? Easy. Clear what I do with the rate region in each step. Okay? Well, if you do that with that list of 700 or 7,000 MDCS regions, and you try to look at there are about 5,500 of those equivalence classes of MDCS regions for which scalar binary codes don't suffice. Using those operators, those very simple ones I just drew, there are only 12 in that 5,500 that are contained in all of the 5,500. So that's nice. I can now look at those. But again, it's pessimistic. It's prescribing things you can't have. It's not describing a rate region of a big problem. It's just saying, well, you can't exhaust the rate region with that class of codes because you have this small problem contained within it. Okay. Let's look at the combination operators. Okay. Do you see why it's clear now? You're just taking two disjoint networks, you paste them together at one place, and not end to end. Okay? No issue here. All right? Very simple combinations. By the way, end to end is complicated. If you want to take a sink and make it a source, you have to worry about dependence of the information at the sinks. But we think we can do it for linear codes. And we have a new operation that we're introducing for that. It'll go to ISIT this year. Okay? But these are all very easy. I merge two edges, right? So that involves creating a new node. This is essentially the old edge. This is the old edge, and then I just have edges coming into that new node. I have source merge, identify two sources with one another, use the same input on the two networks, right? Node merge, take two independent networks, take the node, draw it as if it were the same, okay? And sync merge. All of these are very straightforward, as long as you're doing most of them only one at a time. Some of them you can do more than one at a time. No problems. Okay. Rate region is basically a direct product of the two rate regions. Okay. Well, that's okay. So it's easy to draw networks where you get blinded just because they look so complicated through these operators. So here's a series of this trivial combination operators. Here's a big network. Here's the networks I put together to make them. Here are their rate regions, and here's the combined networks rate region. Okay. But remember, those operators are pretty simple. All right. The big power comes with the way that they mix with the embedding operators. It's hard to see, but I don't really need you to read the labels. Just look at the picture. Okay. The idea is, suppose I start with all networks. It's on the next slide too. Okay. There's one 1-1 network. One source, one edge. Right? It's a trivial network. Right? There's one 2-1 network. Okay? And there are 4 1-2 networks. All right? So if I do all possible combination operators between them, there's no way I can reach this 2-2 network. No way. This doesn't happen. Okay, you can list everything you get. But if I do those combinations, and then I embed, and I do combinations of the embeddings, and I embed, and I do combinations of the embeddings, all through this process you contract the rate region. Okay? And I can get this 2-2 in terms of those simple ones. So in essence, this 2-2 is actually equivalent to the collection of those simple ones I put together through that series of rate region operations. So for this, we have the notion of partial network closure. Okay? What's the idea here? I'm going to do all possible combinations of and embeddings. I'm growing this seed. I start with a seed list of networks. Okay? Say the 6 smallest ones I just mentioned. Thanks, man. Okay? And then I'll do combinations. I'll do embeddings, I'll do combinations, I'll do embeddings, but I'll make sure that I never exceed a certain cap size. Okay? And so if I do that, then I can keep repeating this process until my set doesn't change anymore. Okay? So let's look at that. I did that with the 6 smallest networks. And I used a cap of 4 sources and 4 edges. And remember, these are equivalence classes. This is not with isomorphs, this is without isomorphs. Those 6 smallest networks are actually equivalent to more than 11,000 4-4 networks, okay, using this 4-4 cap if I use both combinations and embeddings. Okay? And furthermore, as you increase the cap for a given size, you get more and more networks of that fixed size. Okay? And it's also really important to observe that you need both the embedding and the combinations operators, because with combinations operators you have much smaller numbers. Okay? So that's a summary for this network coding part of the talk. And thank you for coming. So what did we do? We introduced rate region software. We talked about how it worked. We formalized notions of problem minimality and symmetry. We talked about how to exploit symmetry in converse and achievability calculations. We described a rate region database that's available to anybody who wants it. We described a series of operators. We explained how that organizes the database. Okay, and the sky's the limit here. There's really a lot you can do. So we anticipate the next issue to handle is the coverage. Like how much of the space of possible problems can I hit with a given size, all networks of a given size, with these operators? I'm going to start formalizing that. I think group theory will actually be useful there as well. You'll think of the operators themselves as elements in a group. Okay? So thank you very much. And I have a second talk that I'd love to give at some point on distributed function computation when people are not exhausted. Or I can talk to you offline about it. But maybe I'll take questions now.